So distance and level. So what's the difference between a level and a distance? Or the height of something from a base, right? So level is basically always measured vertically. Distance could be measured any way, how far away you are from an object, right? Uh, so in my solid state class, and we had a bunch of sensors on there, and they put this down for the symbol. Of course, that's totally wrong, right? A device capable, we already looked at this, a sensor is a device capable of responding to a physical stimulus, right? What we're dealing with is the second one, though. This is a device that converts a physical stimulus into electrical equivalent. That's our sensors. But this is what a transducer is, guys, right here. We talked about this, right? A sensor is a transducer, but a transducer doesn't have to be a sensor. So anything that converts one form of energy into another form of energy, these are what we refer to as transducers. A lot of people use these interchangeably, and of course, if you're in a situation where you're dealing with sensors and somebody calls it a transducer, you know, yeah, you might hurt, but you know exactly what they're talking about, right? You understand? But if you was out there, somebody working on a windmill, you're talking about transducers, and then what you're talking about is windmill is a transducer also. In a control system, what things do we need to sense? So what we're trying to do is go through our list, and we're not going to get through there. So we already talked about position. We already talked about speed. We hadn't talked about weight, guys. I don't know why that's marked out. We talked about proximity, and we're talking about level and distance today. So distance, this is the amount of space between two objects, and level is about a vertical distance, height from a base to the top of whatever you're trying to measure, right? You understand? So we measure the level all the time of something. The height at which one material stops and the other one starts. So, in this thing, we're going to look at charging and discharging. We're going to look at liquid levels. These are and two-level control. We'll look at these. This is in the handout that you should have in the discussion section. First level sensor we'll look at is these are ultrasonic sensors. And we've already talked about these. We can use these for a lot of different techniques, right? What does ultrasonic sensors do? They measure the, Yeah, well, it does. It uses echo. Basically, radar works like this. Sonar works on this. It's just what frequency range they operate in, right? So ultrasonic sensors, basically, we can use these to measure distance, but that could also be measuring level. If we measure the top of a material using ultrasonics, then of course we would be using it as a level detector. These are what they use down at the gasoline farm down in Pelham. You know where that's at? Yeah, why wouldn't they use any other? Because it's got gasoline. Those are gasoline storage tanks, by the way, down there. So, yeah. Measures time interval between sending and receiving echoes. We have what we call a transceiver. Transceiver is a term for the transmitter and the receiver inside one unit. Yeah, and all you see, like over on the manufacturing line, if y'all remember, we looked at it. All you see is just a block. Ours just happens to be round. So ours looks like this, and it's got a bunch of threads on it, and then it's got a where we can actually adjust the height, and then it's got a cable on top of it. And then what we can do with our sensors is we can set the span. Now, what's the span? Or sort, it's the distance between what you're trying to sense. So if you got a compressor at your house, or if you've seen compressors, those have a span. They usually turn the motor on at around 70 psi, and then it runs until it gets up to 100 psi. So the span would be what? It would be 30 psi between the minimum and the up one. So what we can do with this one is we can set a lower limit, and then we can set an upper limit, which is usually what we do on most levels, right? You understand? Because if we tried to maintain it at an exact level, then your pumps and everything would be running all the time, because because understand. So usually, even on these hoppers and stuff, that we try to maintain it. We don't maintain it at a height. We maintain it between a height, right? You understand? So a lot of these things have this. So these guys transmit a sound wave, bounces off a surface, and then the sensor itself, either analog. If it's an analog sensor, what's the difference between an analog sensor and a digital sensor? You're going to run into both these.
Analog are versatile sensors.
They're going to give you an output that represents a analog value, right? You understand? An analog value would be something that's constantly changing. A digital sensor is going to look at a threshold, right? It's going to either trigger at a certain threshold or not trigger at a certain threshold. So it's going to give you a digital output. It's either going to be what? On or off. Analog is more accurate. But when you bring an analog sensor into a computer, the analog sensor is extremely accurate, but your computer might not be, right? You understand? Because what we have to do is we have to go from analog to digital. So we go through an analog to digital converter, and the resolution of your converter has a lot to do with it. So this analog to digital converter in this guy, this is what we call a 10-bit analog to digital converter. So it would take the analog quantity and split it up 2 to the 10th, which would be 1024. But remember, what this does, it gives us the number of counts, and that's including 0. So it would come up, and it would only it would take it down and break it into 1023 steps. The little 1214s that we have, those things have 12-bit analog digital converters, so it would be more accurate. So it would be 2 to the 12th minus 1. What's 2 to the 12th? 4096. So it would take it and divide it into 4090 to 4095 steps. I did that in my head, by the way. Y'all know that, right? I've been dealing with computers a long time, so I can go all in my head. I can go all the way up to 2 to the 16th, but that's just because I've been dealing with it a long. Yeah, that's basically it. You know, it's just like, yeah, sure. So the 1214 would give us a more accurate representation of the analog value we're trying to measure. This guy right here is still good, but okay, that makes sense. So analog have the ability to be more precise on what we're trying to measure, right? The digital is either going to be usually on a threshold. These digital sensors sense at a threshold. Probably most of our sensing elements themselves are actually analog. So most of our sensors, not all of them, our level sensors are just switches. So you'll have the sensing element. Oops. Element rich, yeah. And then after that, you would take this inside the sensor and you would go to a analog to digital converter. And these are usually 1-bit converters, which means what? They're either what? on or off. So a lot of our sensing elements themselves are, and some sensors give you the ability to set the threshold. So that means you can come in and you could actually do what? You could actually determine where it switches between a 1 and a 0 or vice versa. So ultrasonics can be designed to sense distance, movement, levels of solids or liquid, speed or direction. The only problem we have with ultrasonic sensors is how much absorbance does this material that we're trying to check, how much of the signal does it absorb, right? And of course, just listen, the military planes that we have now, most of them absorbs the frequencies of radar, and it makes them almost invisible, not totally invisible, but almost invisible. I think they say the one, I think they said it has the radar signature of like a bird, and that's a lot. That's a big plane. So limited by the surface shape. So the F-111, what they did is not only did they do energy absorbing covers, it had all its surfaces were at angles. So instead of hitting it and bouncing off, it would do what? It would spread it out. Of course, y'all probably seen these planes, so y'all understand what I'm talking about, right? So this is the one that we'll look at. This is the one we have on our manufacturing line. It's very similar to this. This is the one they use to look at things in your body without using X-rays. Yeah, babies, they used one on me because they were trying to check to see if I had any blockage in my vessels, because I lay on my back for about 6 months, guys. So they would check me just to make sure that. Photoelectric. So we know about photoelectrics. So here we can we know when light hits something, what we actually see is not the light it absorbs, we see the light it reflects. Different materials reflect light, and we know the speed of light pretty accurately, right? You understand? So we can use the speed of light, how long it takes to get back. We could also use that to detect distance. In fact, that's what a lot of the police departments have gone to, because people bought these radar detectors and put them in their car. Now they use laser, right? And they'll shoot that laser beam, huh? Yeah. Yeah, of course. When's the last time you saw a highway patrol out on the interstate? I don't really, between here and Tuscaloosa. Oh wow. Yeah, they like to get in that median right there. Yeah, well, they passed a law where you got to have a certain number of population in your city before you can get out there, and Bessemer meets that. So we have triangulation. Triangulation transmits at measures the angle of the reflected light to determine the distance. Time of flight. This is the one that operates very similar to ultrasonic sensors. This measures the time it takes a pulse of light to return to the receiver. Pretty straightforward. So this is triangulation. So basically, we shoot a light beam, it bounces off the surface, and then we have several rays in here that senses up the light, and depending on where it strikes, it indicates the angle that it's reflected from. Pretty straightforward. Yeah. And then, of course, we have a time of flight. This works exactly This works exactly like ultrasonics. Then this is the math formula down here. Y'all got to remember that, right? They could literally calculate that. The sensor would have to do what? Would have to calculate that just using a little bit of math, right? Yeah. Yeah, it'll give you an LRT. It'll give you an actual value, right? That would indicate the actual. Yeah, I don't know it either. The more if it gives you a value, then I don't know if it's probably stereo because if it's parallel, there's a lot of wires. A span, yeah, that's what we call a span. Where it's true, where it's true and false. Now remember, these guys are going to depend on what? Like ultrasonics. What does ultrasonics depend on? Yeah, but it also depends on the shape of the object, right? So usually ultrasonics is looking for a fairly flat surface, and then of course how much energy does the surface is hitting absorb. So this guy would have problems with extremely dark objects, right? You understand? Because it wouldn't do what? It would absorb more light and reflects back, so it would have those. But lighter colors, this guy would have no problem with them. Of course, here's ultrasonics. This thing looks like it's out of. We have digital detectors. This is what we're going to use, by the way. And then we have continuous level detectors. These would be analog. Everybody okay there? The one we have is digital. And it's just going to be a float. It's a very simple one. So ours works kind of like this. We actually have two of them. I hope my camera cuts off this time, guys. I've checked it and it did, but that don't mean anything. So this is the one we have, and it's actually got two sensors on it, and it uses a magnetic reed switch. So these are actually magnets, and then the reed switch is here. On this one, the reed switch is inside the actual tube, and then the magnets are on this guy right here. Okay, and that's all it is to it. So this one, if we mount it like this is going to look for it to be at a certain height, right? But remember, on this one, we can also mount it what? So if we mount it like this, then it will look for it to drop below a certain height, right? Okay. This one, we can literally change the way it sees it between a normally open and a normally closed by just snapping this off and flipping this around. And all you're doing is just changing the position of the magnet. So this one way the magnet would be on top of the reed switch, so the reed switch would be closed. The other way, when you flip it around, the magnet would be away from the reed switch, and it would act like a normally open, right? That makes sense? I'll let you take this off. Make sure you don't what? Lose it. Yeah. So this one you really don't need the wiring diagram because it's pretty obvious which numbers these guys come down to. So one reed switch comes down to 1 and 2, and the other one comes down to 3 and 4. These are going to be digital. Are we okay? Any questions on that one? So these are just different forms, so it worked that time, of what we call discrete types. So the first one over here is used a lot. We just put a float inside there. When the material raises up, it raises the float, and it's going to trigger something, right? Here they're using a limit switch. A lot of our sensors, we combine two things to come up and get a sensor. So here we're using a float to detect the level, but the float is not giving us an output. We're using it in conduction with a limit switch. Yeah. So I'd say some of our sensors. The other one is just a photoelectric sensor. It's shooting through a beam through here, and when the gets up and blocks the beam, it would tell us. So this guy would be kind of like our reflective sensor that some of y'all are having problems with. This guy right here is true, right? Y'all understand? When the level is low, and it goes false when the level gets up above it, right? You understand? So some couple of y'all had to come in and swap your contact around because this, this is a resistive probe. This will have to go through an anti-D converter. What it literally does is it's basically bringing the liquid up into the two resistive probes, and then it just depends on the conduction of the material. There's very little material that don't have some conduction characteristics, especially liquids, right? You understand that? Just about all liquids have some conduction to it. So what happens is when the liquid comes up and gets between these two rods, what these rods are basically doing is just once the liquid gets up there, we have current flow between the two rods. And then my sensor would do what? Just measure off where we have the threshold set at. This could be resistance. We could also do this with capacitance. Okay. These are some more. So we have a float switch here. They're using what is the actual sensor that senses the height. Oh, y'all can't see it. Oh, y'all can't. Yeah, it's using a potentiometer. Yeah. Here, what they're doing to measure the height is they're actually measuring the what? Pressure. So the higher the liquid, the more weight it has, right? Puts more pressure on our pressure sensor, and then we translate that over to a level. This is actually measuring what? Weight or the load. So the more liquid you have in there, the heavier it is. And of course, the weight would be proportional to whatever we're measuring. This would be either resistive or capacitive. So capacitance, by the way, this is a real popular way to measure fuel in an airplane fuel tank. Just use a capacitive probe. The airplanes that I worked on in the Navy, these use capacitive probes. And what happens is when the liquid gets up between the two probes, it changes what we call the dielectric constant, or the opposition between the two probes. And then they measured that, and that's why we actually got a fuel. And it was really cool because they had, I think, we had what we call a wet wing plane. So the plane actually carried fuel in its wings, and then it had like a 5 tank, tank. So this plane could stay airborne for well over 14 hours. I think the B-1 bomber, also the F-111, the F-111, which are also the B-2 bomber. Which one's the newest one? The split wing. That's the B-1, right? F-22 too has got the coating on there. It's hard to detect. So I worked on T3 Orion, but and we use this. And, what was neat is that they sunk all the tanks together. They averaged the tank. So if the plane was turning, these guys would fill up on the left, and these guys would be empty, right? You understand? But they sung them all together. So it's really, no matter what attitude the plane was in, it still gave them the same fuel quantity. But we used capacitor probes. So every time we replaced the probe, we had to recalibrate the fuel system. We had to recalibrate the fuel system because there's no way in the world two probes could be what? Exactly the same. Right. That'd be like all the cars out in the parking lot have exactly the same mileage on them. What would be the odds of that? Probably. And then ultrasonics is what we've already said. So we have a lot of different ways to measure these. These would be analog, right? All these would be analog. These would actually give us a quantity that represents the level of what we're trying to measure. Are we okay? Oops. Oh, by the way, y'all know there's a dictionary up on the website inside the course content section. So it's a really good place if it on your review for your test. It just says know the meaning of, right? Yeah. Really? Okay, I'll get it up next week. Next Wednesday, I think, is our next test. You ever 4 classes, guys? 5 for the first one, 4 after that. We're out Monday, yeah. Veterans Day.
We got next week, we got 2 weeks, and then we got a whole week, right?
By the way, the SACS team is going to be on. We're going through accreditation this year, by the way. If y'all hadn't heard, the SACS team will be on our campus Tuesday, which won't affect this class. Thank goodness. It shouldn't. They're supposed to be on the Bessemer campus on Tuesday, and then they're supposed to be on the Birmingham campus all day on Wednesday. And Thursday they're supposed to wrap things up. So if you're in any Tuesday classes, you might have a visitor. So this is some term to understand. Charging systems. What's a charging system? So y'all got this. So let's y'all looking up. So hopefully y'all got it. If you ain't got it yet, it's up here on the desk. Yeah, but if you finish the experiment 3, you need another experiment to work on, right, Alex? Or you probably would like to go home, right? Yeah. So charging system, what's a charging system? I'm going to ignore that. Discharge system. All right. In a two-level system, this is where we're going to try to maintain it between what? 2 levels, right? When we get our level sensors, we should be concerned with motion. We'll look at that because the problem we have is that levels move and change, and liquids especially have a tendency to kind of slosh around and have waves on, right? And if we didn't have something to do with that, then our systems will be cutting on, cutting off for a little while. So we'll look how to do that with our sensors. And if we need to make sure we understand that when we buy a level sensor, if we got it in a corrosive environment, we got to make sure that the sensor that we buy is rated for that corrosion, right? It's just like conductors. Conductors are rated in the amount of amps they can pass. We call it ampacity. Insulators are designed to keep the push in, right? You understand? Jackets are designed on what environment the conductor is going to run in. So sometimes your insulator and your jacket are the same. Sometimes they're totally different. So if you ever get most cables, you know technically what a cable is? Usually has 2 or more wires inside a common jacket, and then the insulators, the conductors will have insulators, but that piece of plastic or whatever they wrap around, that's the jacket. And that jacket is not in there as an insulator. It's in there to determine what environment that cable can run in. Right? That makes sense. What else did it say we need to consider when we buy these things? The density. All solids have a certain density. Capacitive level sensors are designed to detect different amounts of density. Physical state of a liquid depends on the type, temperature, or condition of any liquids. We had to compensate for temperature on scales. The scales that I worked on, the digital scales I worked on, used a resistive. What determines the resistance of a conductor? Yeah. Distance it travels, right? First, we'll start off with the material it's made out of, and then the physical size of it, right? And the distance. What's the fourth thing? Yeah, temperature. So we have a device that's used to measure load. It's called a strain gauge, and it does this right here. So we can't change the material, so it actually weights. We actually put a heavy weight on a piece of wire, and it basically is going to make it flatten. It's going to flatten it out, right? You understand? And it's going to shrink the size on this really cool. But the problem is that if I use this right here to measure weight, then by George, I better do something to take care of temperature. And we'll look at that when we get into strain gauges. So strain gauges have to take care of temperature. We buy and sell off of strain gauges. So just about every digital scale or scale that actually gives you a cost, how much cost is done by these devices right here. And it would be awful if we got if we had to recalibrate our scales. In Alabama, think about Alabama. So we had the hottest September on record here, and then now we're below average, right? Yeah, one day. So we got to consider what these sensors does by the physical state. You know, it's things going to change. If is it going to be able to measure different liquids or a level of different solids or stuff like that? Then we're going to take that in consideration. Is it going to move around, right? If we're going to measure the level conductivity, this is where our resistance sensors and our capacitive sensors come into play. So we'd have a problem if we measure different materials that had different conductivity, because it would give us a different reading depending on the material. It doesn't mean we can't do that. It just means we have to make the sensor. We would have to compensate for that, right? Abrasiveness. If we have a sensor that gets inside something that's very abrasive, it can literally do what? It can literally tear the sensor up, right? You understand? So we may here try to use some type of non-contact sensor, like a capacitive sensor or something like that. And of course, how far do we need to sense? This is sort of the way our sensor works. So what we have is we have a magnet inside our float. We call this the float, and then we sensed it with a reed switch. We had reed switches, right? We went over that. We don't really need to. We could. We are going to have to do on our temperature sensor. We're going to use water because it's the easiest thing to do. So we'll have to get in. We'll have to go down to the. Huh? So our temperature sensor, we're going to use hot water and cold ice water. when we get the temperature sensors here, you can just do what with your finger, just raise them and lower them. What's that? They do, and this is you know, the analogy I use is your what? Is your senses. So we have sensors now that sense equilibrium. So we have sensors now that can balance stuff, right? So which is really neat. They got a so almost anything you can sense, we can design a sensor to sense that. I don't think that they can design a sensor to sense hunger, but equilibrium, balance, sound. We got sound sensors. We got, you know. So the first one we're going to do is we're going to start off with a charging system. This explains the charging system really well. So this is the sensor. This is the symbol of a mechanical float switch. And this would be a normally closed switch, right? Everybody okay? So he didn't do a good job on this. This circle down here is usually bigger. So this is the symbol. This is the symbol for a what? No, that's not the symbol for a motor. That's a symbol for a motor starter, right? And this is a symbol for a what? So what does the solenoid do for us? Converts an electrical signal into a linear motion or a straight line motion. I think this is the first circuit we're going to work. I'm not sure. I can't remember if you're going to design a circuit in these or not. If you do, it's probably going to be in lab 3. Lab 1 and 2 usually just gives you circuits that you come up here. And so this would be a charging control. So charging means it comes up and loads up until it does what? Opens the switch, right? A discharging would be a normally open switch, right? And so when your liquid's on, it holds it closed, and then when it drops down, it does what? It opens up. Sorry. And we combine the charging and the discharging to come up with a what? 2-level. Good. Everybody okay on this one? This is not very hard. This is a pretty simple circuit, right? And remember, depending on what you want, you can just do what? You can just turn this thing upside down, right? Y'all understand that? Yeah. So it mounts on our trainer just as equal. So you don't have to have the label up. There we go. So here we're going to most pump systems. You can either run it in automatic mode or you can run it in manual mode, right? You understand that? In case something goes wrong with the automatic system, we still have the ability to control the level. We're going to use a selector switch. So this is a selector switch, and I'll have to read this, right? So how do we read that? So the solid line would be the normally closed, which switches in this one, then it's going to do what? It's going to break this and make it. So automatic switches auto mode. It does what? It closes this one, opens that one, and now we go through a normally closed level switch. So this would still be a what? Still be a charging system, right? Okay. This is all we've done is added this. By the way, when we get to these, everybody's hooked up the motor. Y'all done a really good job on hooking up the motor for the first 2 labs. So when we start getting to these, let's just don't hook the motor up, okay? You need to make sure you put your contactor in there. Just don't hook the motor up to it, or don't hook the three-phase up and the three-phase out. Okay? And it'll make the labs go a little faster. So are you okay on this circuit right here? So that's the last circuit in this lab. This is lab 1. Okay, so let's take a look at lab 2. And look at the circuit here. Make sure you understand these circuits. Oh, wow. Let's don't look at lab 2. I'll come back to lab 2, see if it'll open. Because I know it's okay, because I opened it up. There we go. So this is going to be a discharging system. So I'm still in here, instead of using a normally closed, we're going to use a what? Normally open. So if you're going to use the one that's horizontal, you'll have to flip the whole thing around. If you're using the little one that floats up, you just change the tab around from normally open to normally closed, right? Anybody got any questions on this? And then we're probably going to come in. Here you're going to have to use 2 of your level switches. So this guy here is going to set a span, right? So this is going to be a 2-level control. It looks like it. I'm sorry, we're adding a timer. What do we need a timer for? It's an on delay timer. Well, what happens is you got your float up there, and your level and your liquid comes up there and hits the float. It closes. But when it's moving, it's going to be doing what? It's going to be doing this. So what we're doing is we're just adding a little time to give the liquid time. So basically, the level is going to be above instead of being at the very top of the sensor, it's actually going to be a little bit above it. And that way, if it's flopping up here, the switch is already made, right? So what we're going to do is this is going to compensate for the liquid sloshing up at the top while we're trying to move past the sensor. Because it would do that, because when liquids are in motion, they have a tendency to and what would happen if you stopped it? What happened is come up and hit it, and then you get a slosh, it drop down, your relay would come in. So what it would do is it would vibrate for a while. So all we're doing is just adding a little time, right? So the sensor goes true, brings in the timer. The timer lets it fill up above the switch, and now it's sloshing up above that, and it's not going to cause any problems, right? So that's what this is. So. And here we have just one level switch. Charging is almost the same one, right? So we're going to add an auto and a manual position. Everybody okay on that one? Yeah. Okay. And then lab 3, we'll see what they do here. And this should be a 2-level control, right? So 2-level controls, we're going to maintain it between a minimum and a maximum. As long as your liquid's in here, you're okay. If it hits the maximum, you need to start discharging the tank. If it hits your minimum, it needs to start charging the tank, right? So here you'll have to use your first float sensors. So this is not anything. This is just showing you the way the system's set up. So we have a normally closed. We have a normally open. So if you get below the level, what's going to happen? It's just a relay. Yeah. So yeah. By the way, normally motor controls, these control relays, we usually call them CR, but you have to understand that's a generic name. It's going to be highly unlikely that you get out in industry and look at a print and you're going to see a relay named CR. It's going to try to give the relay a name or a mnemonic basically what it does. You know, so these are just generic names. All you know is that it's a symbol of a coil. So what I'm doing is I'm looking for a contact that has the same name. So this is the contact for that control adapter, right? Yeah. So it's just a name. So this is the normally open. So that means we're not below the level. Now this is not really a normally open. I need to think about that. It's a normally closed held open now. Oh, it's over here, right? So what happens when you do normally closed switches? That's normally closed held open. So what happens is right now the pump, would it be running or not running? No, it's being held open. That's this guy right here, right? So we're here, right? Okay. And then what's going to happen? Yeah, it's going to get up. It's going to come when it gets. Yeah, when it gets down here, when it gets down below it, it's going to do what? Okay, it's going to cut on. It's going to seal itself in. So the pump's going to start running. And then when it hits this one, it's going to do what? Open this guy and cut it off, right? Until it drops down below the bottom one. It's going to cut it down, seal in, because once it seals in, it'll open up as soon as the liquid gets there. So you'll see how this works. Okay. So one of y'all is going to have to do what? Somebody's going to have to hold that one open, right? So there looks like there's absolutely no design on this one. So this will be the last circuit, and this is supposed to be what we call a two-level control. Y'all got any questions on the operation of this circuit? Yes or no? Huh? No, the CN is a relay. Okay. So what we're doing is the way this is drawn, we'll have to look at it this way. If I can figure out how to get my drawing up. There we go. So what we're doing is we'll start off with the liquid down here. This is held open, so that means this switch will close. That'll close this switch right here. We got power all the way over to CN. CN will energize. When CN energizes, this contact will close. M will come in, right? That'll seal that in right there. So this guy seals in. So now we got a secondary path for current to get over to our relay. Then when this comes up here and gets up above this switch opens. But nothing's going to happen. Why? Because we sealed it in what? Around here, right? Y'all understand? Okay, so the switch opens. Here comes the level. Comes up, comes up, comes up. Hits this float switch. What does it do? It opens. That opens this right here. What does that do? Drops out CN, right? CN will drop out. CN drops out. M will drop out, and the motor stops. And the motor does what? Stops, right? Because it's up on this one. We start using our liquid, and it starts doing what? It dropping down. When it gets down below this one, this closes again. Does what? Brings in CN. CN closes. Brings in M. Seals in, right? Make sense? Yes or no?
But doing this is gonna be a whole different scenario here.
But notice this guy here is drawn, and this is not a normally open. Now this is a normally open, but it's being what? According to this diagram, because they have it in this position right here. Normally what we should start off with is down here. So when it's down here, this float does, this guy's going to do what? It's going to close, right? Okay. And if this closes, it's going to close this contact right here. If it closes that contact right there, then we have a path right there, right? Which causes what? That got to close. Now what's that going to do? It's going to bring in our motor. Our motor starts running liquid, but as soon as this comes in, it's going to close that contact right there. So what did you just do? It just sealed itself in, right? Just like y'all did in motor control. Standard seal-in circuit, but this seal-in or this memory circuit is done automatically once we start this thing running. So as soon as you put power on this thing, guys, something's going to happen, right? So it's going to come up and run. As soon as it starts running and the liquid level gets above this switch right here, what's going to happen down here? This is going to open. As soon as it opens, it's going to break this path right here. It's going to cause this to drop out. It's going to come up here. This is going to open. It's going to cause this to drop out. And now because we got up to this level right here, right? And as soon as this opens, the motor cuts off, and we're pumping liquid out of this tank. So we start pumping this liquid. Anybody that's got an air compressor has seen this almost exact same circuit right here. That is a charge discharge system. But we're using a pressure switch in that one. What we're going to do is we're going to maintain the level in this tank somewhere between where? Somewhere between here. If it gets below that level, we're going to pump it back up, right? If it gets above the level, we're going to have to stop it. And we're going to have to make sure that our pump that we're using has the ability to pump more than we're using, right? Consideration. You got a compressor. If your air tool needs more air than your compressor can put out, then your compressor is going to run forever. Once it drops down, if your air tool needs more flow than your compressor can actually provide, then your motor is going to try to run forever. And those are not continuous duty motors. Those are what we call intermediate duty motors because they're designed to do what? Cut on and cut off. So if you run your compressor all the time, then what's going to happen to the motor on your compressor? You're going to burn it up. So if y'all got questions on this, you need to ask them now. This is why we're going over every circuit. Every circuit, we're going over the operation. I mean, it's just so what don't you know? So this is very similar to some of the circuits you hooked up in motor control. Here, instead of using push buttons up there, we're using what? We're using sensors instead of push buttons, but it works exactly the same way. So this is a level control, right? Everybody okay? So on this one, you don't have to design the circuit like you did in the first circuit on proximity sensor. No, there's no design in this one. That's the last circuit. Yes, they're on the test. Yeah, they're on the test. What's that? No, that test every Wednesday, the first Wednesday of the month. Yeah. Yeah, first Wednesday of the month. Supposed to be the first Wednesday. This one is not bad. Y'all ever been on the Birmingham campus when that thing goes off? It's at